Hey everyone, today we'll be looking at 222 count complete tree nodes. So, this question is from the Explore card of Google and it comes in trees and graph section. So, let's start the timer and try to complete this question in less than 15 minutes. At least come up with a pseudo code for this problem. Okay, given the root of a complete binary tree, return the number of nodes in the tree. According to Wikipedia, every level except possibly the last is completely filled in a complete binary tree, and all nodes in the last level as far as left as possible. It can have between 1 and 2 raised to h nodes inclusive at the last level h. Design an algorithm that runs in less than O of n time complexity, less than O of n time complexity. Okay. So we have 1, 2, 3, 4, 5, 6. Return the number of nodes in the tree. Okay. So if we have to return just a node, then we can either use BFS or DFS. Yeah, or just a DFS. So it's pretty simple in that sense. So okay, what we'll do is we'll write a function. Okay, we can just do this, right? If this root is there, if root equal to null, then we will return 0. Okay, and let left is equal to count nodes of root dot left, so that we traverse left, and let right is equal to count nodes root dot right. And whenever we reach a null, then 0 would be returned. Then what we'll do is we'll return back. So there is a node left. We reached to it 0. When we return 0, then we add 1 and return it back. So okay, let's go here. Let's draw a simple thing. Let's rub this guy out. Sorry about that. Okay, okay, yeah. Once we have rubbed it out, so we had 1, we had 2, we had 3, we have 4, we have 5, and we have 6. Okay, if I've drawn that correctly, okay, it was here. Yeah, I've drawn that correctly. And then what we need to do is, okay, so if I traverse till here, then let me do it in orange. Go here, and once I go here, I return 0 to this guy, and then this returns 1. And similarly, this case, it goes 0, 0, it returns 1. Then we need to add 1 plus 1 plus 1 and send it back to this. So this returns 3. And this guy also returns 1. Then this guy returns 0. Then 1 plus 0 plus 1 returns 2. Okay, got it. So at the end, we have to definitely add these two up, the left and right. We need to add this left plus right plus 1, so that uh, we return. Okay, now I guess that should be it. We should be getting answer as 6. If I run this, yeah, so this answer is 6. And if I submit this, yeah, the solution was accepted. So it's a very basic problem, and yeah, like we can then BFS. So the time complexity of this would be of n, where n is the height of the tree. Will be traversing all the nodes from this guy, and we can do this with respect to BFS or DFS, but the time complexity of it would be same. Yeah, and I don't know if design an algorithm that runs in less than O of n time complexity. I'm not sure if how to do that, but if we go to editorial, like we linear time, binary search, approach 1 doesn't profit from the fact that the tree is a complete one. Okay, complete one. So the main thing was complete in a complete binary, every level except possibly the last is completely filled, and all nodes in the last level are as far as left possible. That means that complete tree has 2 raised to k nodes in the kth level if the kth level is not the last one. Okay, got it. The last level may not be maybe not filled completely. Yeah, that's true in the last one, because in this case the last level is this guy and it is not completely filled. Okay, so hence in the last level the number of nodes would vary from 1 to 2 raised to d, where d is the depth of the so okay, 2 raised to d. Now one would compute the number of nodes in all level, but the last one, 2 raised to d minus 1. That reduces the problem to simple check of how many nodes tree has in the last level. Yeah. So how many nodes in the last level have to be checked? What is the best time performance for such a check? Let's start from the first question. It's a complete tree and hence all nodes in the last level as far as left possible. That means that instead of checking the existence of 2 raised to d possible leaves, one could use binary search and check log to the log 2 raised to d is equal to d leaves only. Okay, how? Pivot. Let's move to the second question and enumerate potential nodes in the last. Return 1 if d is equal to 0, the number of nodes in all level, but the last one is 2 raised to d minus 1. The number of nodes in the last level could vary from 1 to 2d. Enumerate potential nodes. Perform the binary search by the node index to check how many nodes are in the last level. Use the function access idxt root to check if the node with index idx is access. Use binary search to implement access as well. Return 2 raised to d minus 1 plus number of nodes in the last level. Compute depth. Yeah, the same thing. The hard fault. I solved it in often and was beaming with pride until I saw the binary search approach. So yeah, the same thing happened with me. Mm-mm. Yeah, this is interesting. Um, Often has Leetcode done it by any chance? YouTube count complete tree nodes.
Hello guys, so today we are going to see a problem from Leetcode called count number of nodes in a complete binary tree. So the problem statement is simple: given a complete binary tree, count the number of nodes. So basically complete binary tree is a full binary tree till h minus 1th level, and at the last level the nodes will be filled from left to right. So this is a complete binary tree, and this is not a complete binary tree because it is not filled from left. The last level is not filled from left. So a simple solution would be to count all nodes by traversing the whole tree, and it will take O of n times. So can we do something better? Can we use some property of complete binary tree? What if I give you a full binary tree? Will you be able to count the number of nodes? That is pretty easy, right? I will give you a tree. We will just calculate the height, and we will use the formula 2 to the power h minus 1. So here height is 3, number of nodes will be 7. The time complexity to count the number of nodes in full binary tree will be O of log n because you have calculated the height of the tree. So can we use the same concept in complete binary tree? Given this complete binary tree, we just need to extract all the subtrees which are full binary trees. Let's see how. So initially you will be at the root. Now you will go left and calculate the height, and similarly you will go right and calculate the height. So left height is equal to 4 and right height is equal to 3. Remember that this is not the height of the tree. We are just calculating by traversing leftmost branch and traversing rightmost branch. I will see at this point both the heights are not equal, hence it is not a full binary tree. So I will do two recursive calls, one to the left and one to the right children. So first I will go to left, then I will again find the left height of leftmost branch, and right height of the rightmost branch. And I will see whether left height and right height are equal. Yes, they are equal. That means it is a full binary tree. That means I can directly count total number of nodes in this subtree. So I will return 7 here, 2 to the power 3 minus 1. Now I will go to right children and I will count left height and right height since it is equal. So I will return 2 to the power 2 minus 1, that is 3. So from here I got 7, from here I will get 3. So this will return 7 plus 3 plus 1 because it will count itself also. So total number of nodes will be 11. Let's take another example. This is also a complete binary tree. So I will first come to root node. I will go and find leftmost height and I will find rightmost height. I will get LH as 4 and RH as 3. Since they both are not equal, then I will recurse to both the children. Now I will come to left children and it will again calculate left and right. So my left height will be 3 and right height will be 2. Again they are not equal, so I will recurse to both the children. I will come at this child. Since left height and right height are equal, I can count number of nodes for this subtree and it will return 3. Now my recursion will come here and it will check whether left height and right height are equal. They are not. So again it will go to left of this children. So if you can see, ultimately our algorithm is finding what is the rightmost node at last level, right? So from here it will return 1, this will return 2, and this will return 2 plus 3 plus 1, 3. Similarly I will go to right child. Here I will, so total nodes will be plus 1. That is the time complexity of this approach. As you can see, we are calculating height many times, so it will take log n time to calculate height one time. Now how many times I am calculating height, that will depend on when I am getting rightmost node of the last level. So in worst case I might go to the leaf node, so it will also take log n. So the time complexity will be log n into log n. Let's see the code. So here I have three functions. This is the main function. So initially I'm checking my left height and right height. That means if this is a tree, so I am calculating this part and this part. This is LH and this is RH. Now I am checking whether LH is equal to RH. If it is, then that means I have found a subtree that is full binary tree and I can directly calculate the number of nodes. Otherwise I will recurse to left part and right part counting that node also. So this is it for this video. Thanks for watching. Full binary tree and I can
Okay, so let's see. I understood the problem, what it's trying to do. What they're trying to do here is, let's say if root equal to null, then return 0, then let left height, we need to check left height. So left, they are, let's call it LH, left height function get left height function would accept root dot left and let RH is equal to get right height root dot right, and if LH LH equal to R where the hell is h? Then what we do is return math.power LH plus RH raised to the power 2 plus 1. That's what we do. Else, if it is not equal, then we search for count nodes at left hand side, root dot left plus count nodes on root dot right, and we send plus 1. So function get left height root, yeah, will be just passing the root, right? If root equal to null, then return 0, and return get left height will be always going to the left side, and then plus 1 will be counting that same thing, and get right height root. Then if similar thing, if root equal to null, then return 0, then return get right height root dot right plus 1. Oh, why did I do plus? Because they are similar, right? We don't need to do plus. I'm doing plus 1. Oh, here we have to do minus 1. Dot floor JavaScript base and exponent, right? So I am using a wrong base and LH. What the hell? Do I need to still do this? Or is it okay? Oh, we have to send the root itself, not root. Root dot left. Oh, Okay. So this is interesting. So what would be the worst case scenario? Okay, log to the let's see where he was calculating.
Example, this is also a complete binary tree. So I will first come to root node. I will go and find leftmost height and I will find rightmost height. I will get LH as 4 and RH as 3. Since they both are not equal, then I will recurse to both the children. Now I will come to left children and it will again calculate left and right.
Okay, got it. Got it.
So my left height will be 3.
Got it. I got it. This is good question. This is a good question. Even though it's easy, the trick part is understanding how we can use the this complete com it like the fact that it is a complete binary tree. So yeah, that's interesting. We need to also like this. Why did they shift the like button down? I don't get this. It should be here itself. In star market and add this to the tree, right? Yeah, the pretty interesting question. Okay, cool. So in the explore card, we can also um, make this, mark this as completed. Internet is pretty slow, guys. Sorry about that. Okay, cool. Accepted. I guess Google likes to ask a lot of tree questions um, rather than the um, questions that you know deals with graph. Yeah, these are mostly tree questions. So we'll focus on that, and then I guess we should also be focusing on array and string. Array and strings are one of the most asked questions um, in the uh, in the stack of Google questions. So yeah, we'll also look at those question, interview, or even jams. Okay, cool. For this session, that's it. If anyone is watching these videos and if you have any idea of what one should expect in front-end interview, phone interview, front-end phone interview at Google, please let me know. That would be really helpful.